In this video, we shall look at a problem associated with the calculation of period of simple harmonic motion. Problem 1. Assume that you have the following simple harmonic system. So this mass M is connected on either side by two springs. The one on the left has a spring constant K1, and the one on the right has spring constant K2. So let's assume that this mass is displaced slightly to the right, a distance x from the equilibrium position, and released. It will oscillate. What is the period of that oscillation? The net force on this mass M consists of two terms. The force due to spring 1, that is that spring, plus force due to spring 2, that spring. So let's calculate these two terms. When the object is displaced at distance x from the equilibrium position O, spring 1 is stretched by that same distance, namely x. So the force F1 due to spring 1 on M will tend to pull the mass M to the left. So we write F1 equals minus K vector x, where this vector x is the displacement vector. And since the displacement of the mass is to the right, we write vector x as x times I hat, where I hat is the unit vector along the x-axis. Let's not forget the spring constant of spring 1 is K1. So putting everything together, the force due to spring 1 on mass M is minus K1 x I hat. What happens to spring 2? Spring 2 will get compressed by the same amount. So the force it exerts on mass M will also be going leftward. So the force spring 2 exerts on mass M is given by minus K2, where K2 is spring 2's spring constant, times the displacement of that mass. And using this expression for the displacement, you get F2 to be minus K2 x I hat. So there you go. We have net force on that mass M to be minus K1 plus K2 x I hat. According to Newton's second law, this has got to be mass times the acceleration vector. Now since the force, the net force that is going in the leftward direction, the acceleration is also along the negative x-axis, namely in a leftward direction. But we know the acceleration, the magnitude of it, is given by omega squared times the displacement, where this omega is the angular frequency of the oscillation. Since the direction of the acceleration is leftward, we can write the acceleration in the following manner: minus mass omega squared x I hat. Now let's compare this term to that term. We know they are the same. So writing K1 plus K2 x equals m omega squared x, x goes away. You see the angular frequency omega is quite simply K1 plus K2 over mass square root. However, we are interested in period. Angular frequency is related to period in a following manner: 2 pi over period. So that means period is 2 pi over angular frequency. So using the expression that we have just obtained for angular frequency, you get period for the system to be 2 pi times square root mass M over K1 plus K2. And that's the final answer to this problem. What about this oscillator, this particular system? As mass M is stretched, let's say, to the right by a distance, say, x from its equilibrium position O, the system will start to oscillate. What is the period for such an oscillation. You have a couple of springs that are connected in series. The first one has a spring constant K1, the second one has a spring constant K2. Let's look at spring 1 first. The force due to spring 1 F1 is given by minus K1 X1, where X1 is the displacement of just spring 1, or the amount it stretches as mass m is displaced rightward by distance x. And the direction of this force F1 is obviously to the left. Likewise, the force due to spring 2 F2 is given by minus K2 X2, where X2 is the amount of stretch of spring 2 as m is displaced to the right. The springs are connected in a straight line, so that means these two forces must be the same. If they are not the same, then the connection would break. Now let's write down the force on this mass m. Let's call that force F, and that is just minus K prime displacement vector x. And let's take that displacement vector to be the sum of x1 plus x2, as should be the case. So all these forces, F1, F2, and F3, they act along the same line, so this must be the same to that, and that must be the same to that, as we have found out here. So let's write everything down. F equals to F1 equals to F2. The idea is to determine this K prime, which can be taken to be the effective spring constant of the system. So let's write down the equations. The magnitude, or the scalar form of the equations, K1x1 equals K2x2. That is from here. We also know F1 equals to F, so K1x1 equals to F, which is K prime x1 plus x2. And we also know F2 equals to F, so K2 x2 equals K prime x1 plus x2. We can use these three equations to determine the effective spring constant K prime in terms of K1 and K2. So let's do just that. Let's use the middle equation. It reads K1 times x1 equals K prime x1 plus K prime x2. However, x2 equals, from this equation, K1 over K2 times x1. So you see x1 goes away like that. K1 equals K prime 1 plus K1 over K2. And solving for K prime, we get K prime to be K1 times K2 over K1 plus K2. So that is the effective spring constant for this system. Having found the effective spring constant, let's go back to the equation above. So this force F is the net force on this mass m, and it's given by mass times the acceleration vector. And we know the acceleration vector is minus omega squared times the displacement vector. And in this case, the displacement vector is x1 plus x2 vectors. Putting this expression in here, we get the net force to be minus m omega squared vector x1 plus vector x2. Equating these two expressions, we get K prime equals m omega squared, where again omega is the angular frequency that describes the oscillation of this system. So let's substitute the expression for K prime that we have written there. K prime is K1 times K2 over K1 plus K2 equals mass times omega squared. Now omega can be determined from this equation. So from this line, we see that the angular frequency in terms of K1 and K2 and M is just K1 times K2 over M times K1 plus K2 square root. But since omega is also given in terms of period as 2 pi over period, we can solve for period as 2 pi times the square root of M K1 plus K2 over K1 times K2. And that is the final answer for the period for the oscillation of the system. Thank you for watching.